Okay, welcome back. For our final presentation this hour, we will hear from Manan Mittal of the University of Illinois Urbana-Champaign, and he's going to tell us about 3D printing head simulators and what they can be used for.
Thank you for the introduction. My name is Manan. I'm from the University of Illinois in Urbana-Champaign, and I'm going to talk about 3D printed heads and why we think they're useful and in our research and in research in general. This project has a long history, actually. This is a wooden head that we printed many years ago that was supposed to mimic human talking. And on the left, you see me holding one 5 years ago that was about a head that can move left and right in response to a sound. So this entire project is actually student-built. I'm just the teaching assistant for the class, but none of the students will come here to present their work, so I'm doing it for them. So why would we need acoustic head simulators? Well, to assess algorithms that work for human beings, we want to process the sound that we receive at our left and right ears. To do that, our acoustic head simulator must be able to simulate that as well. So data sets that we create should have these left and right cues that human beings use to localize sounds and detect where people are talking from. These are mostly called the interaural level differences and time differences. Quite obviously, the level differences check the amplitude difference in the left and right, and the time difference is how long it takes a sound to propagate from one side to the other. Another reason why we would want to have acoustic head simulators is because humans are not stationary. Humans keep moving as we talk. I can't keep stationary as I try to talk at all. And what we would want to be able to do is study the effect of motion in an algorithm separately from the signal processing itself. So if I were to turn this way, this means the array is kind of bending like that. And if I were to turn the other way, it's like the array is bending like that. But in both cases, I want to be able to separate out talkers that I'm listening to, which is especially important for hearing aid users who need this cue and this processing in order to maintain a conversation in a noisy environment. We did an experiment a long time ago where we set up microphones and moved them in a line, and they swung around. And as they swung around, we tried to maintain beamforming performance of our algorithms and separate out talkers. We did the same thing with a mannequin, where the mannequin was allowed to rotate and move, but we only changed the deformation slightly so we can study motion. Another reason why we would want acoustic head simulator is because we want repeatable motion. For some reason, my video is not playing, but that's OK. I can just describe what happens. The head that's on this spider board will moves across the screen, while that head that you see on, oh, there we go. Thank you. And the other one turns around as if it was a human responding to acoustic cues of someone else talking and moving at the same time. Now, this is really hard to do for a human. If you asked me to do this twice, I'd probably go like 10 centimeters off, which anyone who studies acoustics in a room knows that's too bad. Like, you're never going to get anything good out of it. So acoustic head simulators, they're stationary. We can do repeatable experiments. We can customize them, and they're inexpensive. I can 3D print them. So we have designed a head that looks like this. It breaks up into 3 components, has a dome. We can pick out the ears, select the ear shape and the size, and we have a turret that allows you to do left, right, up, and down. And the idea is just to be able to simulate human motion as much as possible. So why did we choose 3D printing? It's cheap, accessible, affordable, reproducible. Anyone can send out an order today and get a 3D printed ear. And we can quickly prototype different designs of ears and heads. So this is, again, that acoustic head that I said was the wooden version. This is the first version, and that's the latest version that we have today, which sits on a turret, opens up, and has detachable ears as well. These are directivity plots so that we could test how the head performed against human talkers. So this is an older version of the plastic head. But you can see that in the lower frequencies, which is in blue, we actually maintain that directivity pattern that human talkers have. When the higher frequencies are suffering a little bit on the off axis. But that's something that we're working on for future iterations. And maybe if we add lips to our design, we could get some of that spectral shape. Right, so the turret, you might be wondering, robots are not quiet. How can you use them for acoustic simulations? Actually, our students have been working on quiet robots. So everyone is trying to build a robot that is as silent as possible. And this is the turret in motion right now. No human can do 360-degree motion, I know that, but you know, it's cool. And finally, I actually have a head with me over here that we can put together. These are the heads that talk and move. So this is the face. This is where the speaker grill would be. We have a talk box so that you can simulate the acoustic pressures and get a good environment if you'd like. We have magnets to clip on the head. And these are the ears that I was talking about. So you can pop them out and replace them if you'd like, essentially. And the whole thing just clips on. So if I were to just clip it, and then you can put that. Oh shit, sorry. I wish I had a table. But, right. And then it just clips on, and you can close the ears up, and then put the magnet back on, and you're good to go, essentially. And we have driver ports so that you can drive the wires out, and for any additional things you would like. This hole is actually mounted on our turret, so it can move left, right, up, and down. Cool, thank you for listening. And if you have any questions, please check out our blog too. We post all the work that we do over there. Thank you.
Awesome. Well, cool talk, and thanks for showing us your head. So I'm just kind of curious, when you're designing these and 3D printing them, what's like the hardest part to get right?
So for the longest, For the longest time, our problem was actually getting the geometry right. So getting an accurate 3-piece model of the head is actually hard. So the wooden head was a 1-piece model that was CNC'd off a block and made by one student. And then we decided that we'd like a 3D printed model that could actually accommodate for different head shapes. So we made a modular piece. So the geometry was the hardest part to begin with. Now it's going to be the ears, I think, and then the mouthpiece, hopefully.
From the perspective of a whale researcher, and not a human head one, something that we worry about is like Schultz waves, or the way the Rayleigh waves travel along the body of the whale, right? Because it's huge. Is it possible that the plastic isn't like the viscosity of our skin or our cheek tissue, and that might be changing some of the directionality in your plots that you showed, or is this just too short to matter?
So that would affect the received signal at the microphone. What you saw there was if I put a speaker here and played sounds out, what it sounds in an axis around them. What you're saying would affect the received signal. So if I put a microphone in these ears, which we have, then yes, the plastic would affect the received acoustics, and we'd see a difference between what a human would receive and what the plastic head would receive. To work on that is why we have this open area here. So we want to fill it up with gel and things that simulate human density of the human head and things like that. And we're actually working on printing in different materials, so we can test those. And the industry standard devices actually cost like upwards of $15,000, and this is sub $100. So the idea was to buy one of those and now start comparing against them. We actually have an order placed in for them, so we're going to start doing comparisons against industry standards. So we have a good measure. And those are made with plastic too, a lot of them, so we should be good, hopefully.
Thanks so much for the demonstration. We have a couple questions from our virtual audience. The first one is from Maura Shapiro, and she's asking, can you explain why the figures have different humanoid features? They don't seem to participate in the speech production or listening, like noses and eyes.
I'm sorry? The noses and eyes. Oh, because, yeah, we don't need them at all, I guess. They don't participate in the speech production, and the cavity shape is the most important part, and we've already built that in, essentially. So we have a little bump for where the eye would be and a little crevice for where my eye goes in. So we have all that built in, and the nose shape is meant to just simulate the head geometry. I don't know how much the effect of eyes and ears is on the received signal for a human, but I can actually test that in the future on myself and report.
Well, it certainly makes them interesting to look at.
Yeah, exactly.
One more question. This one is from Avery Thompson. Can you talk a bit about some specific results you can obtain by using these models, and how have you applied these heads in research?
Yeah, so my advisor and his student, I guess, Ryan Corey, did a paper a long time ago that used these heads, the wooden version and the plastic version, to test the effect of acoustic face masks on the acoustics of humans. So he did a study where he put face masks on himself, on the wooden head and on the plastic head, to see how the consonants and fricatives that you use in your speech actually propagate throughout the environment, and what losses you incur from wearing that face mask. Because there's a lot of hearing aid users that would actually need that higher amplitude or that clarity in sound. So face masks were used with these heads to study the loss for hearing aid users. And I think that was published in ASA as well, so yeah. Cool, thank you so much.
Thank you. Okay, well, thanks for tuning in this morning. Our next session of press conferences will start at 12:30 p.m. Central Time, and we'll see you then.